Good morning, all of you. This is K. Ishwan from CSC Data Science Department, third semester, section B. Now, my rule number is 6763. So, now I am presenting the topic of simulation of a multi-tier circular queue for real-time task scheduling in Python. So, this is related to the data structures and algorithms. So, first we go through the introduction. Simulation of a multi-tier circular queue for real-time task scheduling in the Python. First, a multi-tier circular queue is specialized data structure which is designed to handle real-time task scheduling efficiently, and it prioritizes tasks across multiple tiers to optimize processing order. This presentation covers the core concepts and design and implementation of this queue structure in Python and highlighting advantages in managing real-time systems with time-critical demands. Here, a multi-tier circular queue is specialized data structure, which is designed to handle the real-time task scheduling as efficiently. It can prioritize tasks across the multiple tiers to optimize processing order. In this presentation, we can cover the core concepts and design and the implementation of how we implement this queue structure in Python and what is the design of this structure and what are core concepts, and here we also highlight the advantages and the managing of real-time systems with time critical demands. So we go to the topic. First, a multi-tier circular queue is an advanced data structure that combines the properties of both priority queues and circular queues. It is primarily designed to handle real-time task scheduling in systems where multiple processes or jobs complete for CPU time. Circular queue. It can ensure continuous looping of elements without needing frequent memory reallocation. Multi-tier concept. Tasks are distributed into multiple queues tiers based on priority levels. Goal: to maintain both fairness and efficiency while ensuring that high priority tasks are executed without delay. Key features: efficient memory utilization due to circular buffer structure and predictable timing behavior suitable for real-time systems. What is a multi-tier circular queue? Is an advanced data structure that combines the properties of both priority queues and circular queues. It is called as multi-tier circular queue. The primarily designed to handle real-time task scheduling in systems where multiple processes or jobs complete for CPU time. What is circular queue? It can ensure continuous looping of elements without needing frequent memory allocation. Multi-tier concept. Tasks are distributed into multiple queues based on priority levels. Goal. The main goal is maintaining of both fairness and efficiency while ensuring that high priority tasks are executed without delay. The key features also we are know. Next, definition and key concept. A multi-tiered circular queue organizes tasks into several priority levels or tiers, each implemented as circular queue. This approach allows continuous cycling through tasks while maintaining order and priority. The circular nature ensures efficient use of memory and time, avoiding the overhead of dynamic memory allocation during the task scheduling. So these are the key concepts of multi-tier circular queue. Next, benefits. What are the benefits in real-time scheduling? So, there are some benefits in real-time scheduling. The multi-tier circular queue improves the real-time scheduling in several ways. First one, predictability. In predictability, each task has defined execution window. Here, the each and every task is defined as a execution of window. Responsiveness. High priority tasks are served promptly. Fairness. Lower priority tasks still get CPU time through cyclic scheduling. Low overhead avoids frequent memory allocation or shifting. Next, stability reduces jitter and latency under high load conditions. For example, in embedded systems, sensor data can be prioritized while ensuring background tasks like logging still execute periodically. So these are the benefits in the real-time scheduling. Next, when we compare with other queue structures, so there are so many queue structures in the data structures. First type, first in, first out. Next, priority queue and round robin queue. First, we go to the first in, first out queue. The characteristics are process tasks in order of arrival. Limitations: no prioritization because of we those who are come first, they can serve first. So first in, first out. Here, advantage of multi-site circular. What is the advantages compared to FIFO is adds multi-level priority plus cyclic flow. Priority queue. It can strictly processes highest priority. It can cause starvation of low priority tasks and balances fairness and priority. In round robin queue, equal time for all tasks and lacks urgency differentiation and combines round robin fairness with priority awareness. Next, what is the design of the multi-tier circular queue? Each tier acts as an independent circular queue, maintaining its own set of pointers. First, the front. There are so many pointers and the other components. First, front pointer. In front pointer, it can indicate the first task in the queue. Rear pointer indicates where the next task will be added. Next, tier manager oversees switching between tiers according to the priority. Next, components. Here tier 1 high priority time critical task, example interrupts and device control. Tier 2 medium priority regular but non-urgent process. Regular. Tier 3 low priority background task and maintenance job. Here there are three tiers: tier 1, tier 2, tier 3: high priority, medium priority and lower priority. In high priority time critical task, and medium priority regular but not urgent process. Low priority some it only the background task and maintenance jobs can be managed. Next, structure and components of tiles. What is the structure and components in tiles? The queue consists of multiple tiles, each corresponding to a specific priority level. Each tile operates as an independent circular queue with front and rear pointers, managing task insertion and removal. Together, they perform a hierarchical system where higher tiers receive scheduling preference, ensuring critical task prioritization. So, here the queue consists of multiple tiers and each corresponding to a specific priority level. And each tier operates an independent circular queue with front and rear pointers managing of insertion and the removal. So, what is the queue operations and management? Here, for every queue, there is some of queue operations and the management. Here also, the system executes basic queue operations within each tier. NQ operation. Here, NQ operation adds a task at the rear and checks for overflow. DQ operation removes a task from in front and check for the underflow. Peak views the next task without removing it. Management process. The scheduler always checks the highest non-empty tier. If a tier becomes empty, control passes to the next lower tier. Once all tiers are serviced, the process restarts. It is called as circular loop. So here NQ operation, DQ operation. NQ means adding of task. DQ means removes a task. Peak views the next task without removing it. Next, management process. The scheduler always checks the highest non-empty tier. If a tier becomes empty, control passes to the next lower tier. Once all tiers are serviced, the process can be restarted. Next, prioritization and task categorization. Tasks are categorized into different tiers based on priority levels, enabling the system to assign regular resources efficiently. High priority tasks are placed in upper tier, ensuring quicker access and execution. These classification supports dynamic task management and helps maintain system responsiveness, allowing this real system tasks to be handled with appropriate urgency. Tasks are assigned to tiers based on urgency, frequency, and deadline constraints. First, high priority. High priority task, low priority task, and medium priority task. First, high priority task. Real time or safety and critical. Medium priority. Here, periodic tasks that affect performance but not safety. Low priority. Background updates, data logging, and etc. This structure enables dynamic load balancing. When one tier overflows, lower priority tiers can temporarily observe load under control condition. So this is so totally about the prioritization and task categorization. Here, how we categorize tasks: lower, medium, and higher. So this structure enables the dynamic load balancing. When one tier overflows, lower priority tiers can temporarily observe load under control conditions. Next, implementation in Python. So how we implement the Python? It is okay, but how we implement the circular queue in the Python? Python's object-oriented features make it easy to model each queue as a class. Core components. Each tier is an instance of circular queue and all are managed by a scheduler class that controls task dispatch based on priority. Advantages of Python implementation. Here, readable and modular design and easy to simulate multi-threading and concurrency with the threading are essential. supports debugging and visualization of task scheduling. So these are the some of the implementation of the Python. Next, data structures and classes used. The implementation leverages Python classes to encapsulate queue behavior using arrays or lists to represent circular buffers. Each layer is modeled as an instance of circular queue class. Key attributes include pointers for front and rear, with methods supporting enqueue and dequeue operations to maintain modular, clear, and reusable code. Next, algorithm for task insertion and retrieval. Here, task insertion places new task at the rear of the appropriate tier's queue and respecting the circular buffer limits, and retrieval follows priority order and servicing task from the highest non-empty tier first. This algorithm ensures fair and efficient pre-processing while preventing starvation and maintaining continuous task flow in the real-time environment. So it is the algorithm for task insertion and retrieval. Next, handling concurrency and real-time constraints. The system addresses concurrency through locks and semaphores to avoid race conditions. When multiple threads access queues simultaneously, real-time constraints are enforced by limiting task execution times and preempting lower priority tasks, ensuring critical operations maintain timelessness without sacrificing system stability. Next, application and performance analysis. So here there are some of challenges. First, handling queue overflow during heavy loads and preventing of high priority inversion. Low priority task blocks a high one, and reducing context switching overhead and optimization. Dynamic resizing of queues, adaptive priority tuning, efficient lock-free algorithms for concurrency, and using priority hanging to promote waiting tasks. No, the real-time task scheduling scenarios. This queue model is ideal for systems requiring layered priority management such as embedded systems, telecommunications, and multimedia applications. It efficiently handles tasks like sensor data processing, network packet handling, and multimedia streaming by ensuring high priority jobs are processed within the strict deadlines. Performance metrics and evaluation. Key metrics include task queue latency, throughput, and CPU utilization. The multi-tier circular queue demonstrates low latency for high priority tasks and balanced CPU load across tiers. Evaluations typically show improved responsiveness and fair resource distribution compared to simpler DQ implementations and confirming its suitability for the real-time systems. So, challenges and optimization strategies. Challenges include managing queue overflow, avoiding priority inversion, and ensuring low overhead during high load. Optimization involves tuning tire sizes, dynamic priority adjustments, and using of efficient looking mechanisms. These strategies enhance performance, reduce delays, and maintain system robustness under varying real-time workloads. Conclusion. So the multi-tier circular queue offers a robust structure for real-time task scheduling by combining priority management with efficient memory use. Python implementation demonstrates practical applicability and adaptability to diverse scenarios. By addressing concurrency and optimization performance, it provides a reliable foundation for systems demanding predictability and speed in the task execution. So finally, thank you for giving this an opportunity to present the uh, circular queue by using of Python. Thank you.